So good morning to everyone. So I'm Marta Pascoal. I'm going to present a joint work with the other colleagues from Politecnico de Milano, and the presentation is about the shortest path problem for electric vehicles. So in recent years, several governments have adopted policies that encourage the use of electric vehicles in order to reduce greenhouse gas emissions. The percentage of these type of vehicles in Europe has grown from 3% in 2019 to 10.5% in 2020. When compared to internal combustion engine vehicles, the electric vehicles have clear advantages, such as reduced maintenance costs and operating costs, thanks to the lower price of electricity when compared to fossil fuels. But on the other hand, they have a higher purchase price, at least for the time being, and their autonomy is limited due to the limited battery capacity. So the increase in the number of electric vehicles is reflected in an increase in the charging stations that exist along the road network. We can say that in Europe and nowadays there are on average 7.5 electric vehicles per charging station. And this value is still lower than the one that was recommended by the European Union in 2014, which was of 10 electric vehicles per charging station. Still, the stations are much fewer in number than the petrol stations, at least for the time being. So the shortest path problem is a quite classical problem that consists of finding the shortest path in a road network, in our case, from a given origin to a given destination. We are interested in a variant of this problem, which is the shortest path problem for electric vehicles, that we call the electric vehicle shortest path problem, which instead is the shortest path problem where the battery capacity is also taken into account. Because we need to recharge the vehicle while it is traveling. So in principle, we will have to deviate from the classical shortest path whenever we need to reach a charging station. This is particularly relevant during medium or long trips. Those cases, it is important to decide the places or the charging stations where we should stop and how much to charge in each of those charging stations. Also, whenever we stop for charging, whenever the vehicle stops for charging, the charging time can range from just a few minutes to several hours. And therefore, it is common that charging stations are installed nearby some kind of point of interest in order to, let's say, to entertain the driver while the vehicle is charging. So choosing the right charging station or the right charging stations during a long journey may be a very important choice because it can avoid very boring waiting times. So sometimes it is better to take a small detour just to stop at chargers that best represent the user's preferences. Okay, so for instance, so in all for instance, in this case, we may have different charging stations, and if the driver is particularly fond of a shopping mall, for instance, it is natural, or it is more natural, that he doesn't mind to detour the shortest path to stop at a charging station near a shopping mall. Okay, so we need to take that into account as well. So the problem that we want to handle is to plan possibly a trip with possible more than 1 day trip for a single electric vehicle, searching for the shortest path between an origin and the destination nodes that are given in advance, while respecting all the energy constraints and time windows there may be for visiting some of the points of interest, and also maximizing the total score that the user can get when stopping at those points of interest. So, for instance, during a long trip, the user may decide to make stops at certain places, but some of those places may be associated with given time windows. For instance, the driver may need to stop for having lunch, or may need to stop because we are considering a multi-day trip. He or she may need to stop to stay overnight at some place. And there are more or less flexible time windows for those two cases. Of course, the night should start, I don't know, but maybe at 8 p.m. and the lunchtime can vary from noon until 2 p.m., something like that. Okay, so the time windows are defined, for instance, for those cases, and also when we consider the stops, we consider the distance of those stops to the charging stations. We also consider that we can relax the time windows. For instance, we can arrive at a certain point a little bit earlier, but then then the vehicle needs to wait for a maximum time of 45 minutes in order to start charging, if in case needed. For instance, if we arrive too early at the restaurant for having lunch. Okay. So this graph shows the charge of the way how the battery charges along the time. This is a piecewise linear charging function, and due to the minimum parking time of the time slots that we are considering, it is possible that the vehicle must remain idle, so it is parked and charging in one place for longer than what is actually necessary for fully recharge the battery. And in that case, that is why we add this, let's say, the extension of the yellow line. We simply consider that whenever we reach that point, that from that point on, the charge will remain constant. It cannot charge more than that. So whenever the vehicle needs to be charged, the user will spend some time close to a charging station, and we assign each charging station with a score that somehow represents the preference of the user. The score will be a real number chosen from 0 to 5, which is higher when the preference of the driver for stopping at that place is also higher. For instance, in this case, the red vehicle would prefer, or if the purple vehicle wants to stop at the restaurant, a very high score will be given to the restaurant. So we will later on present some experimental results that were chosen, or that were results of tests that were done in a selection of 20 routes created to simulate different trips in Central Europe. This is the summary. These are three of those trips. So this one goes from Geneva to Zurich, and then we can vary the starting time of the trip. In this case, the trip starts at 10, in this case, it starts at 1 p.m. Okay. The fastest route for an electric vehicle from an origin to a destination cannot be along roads that are not considered the fastest for a regular combustion vehicle. So once the fastest route is recovered using a routing provider, the charging stations that are nearby those routes, so that are less than 5 kilometers from this optimal route, are then selected. And the graph used in the experiments that is generated from the set of these nodes is then preprocessed by removing the nodes and the edges that are useless for the final solution. So we have developed several mixed integer linear programming problems, which were solved by Cplex. These models are used to, let's say, to compare the heuristics that I will be talking about next with an exact solution given by these models. So the heuristics that we used are based on the search algorithm for the shortest path problem, and this it's a pretty well-known. This is a pretty well-known heuristic that searches for the least cost path between a source and a destination. The algorithm keeps in memory all the roads starting from the origin, and it extends them, let's say, one arc at a time, until the destination is reached at the least cost. It uses best first search, selecting each time the node that minimizes this quantity here, G of node n plus H of node n. So G is the cost of the path from the origin to this node n, whereas H is an heuristic function that estimates the cheapest cost for going from node n to the destination. So the vehicle can arrive at the same node coming from different roads or from different paths, or even with different amounts of energy or at different arrival times. And therefore, many different states can be associated with a given node. So these different vehicle states are called labels and are dynamically allocated as the algorithm runs. Each label represents a trip between the origin node and a given node, as well as the charging time that must be carried out in the departure node in order to reach the arrival node. So since we want to minimize the travel time, but also to maximize the total score, we change the weights that are naturally associated with each arc of the network in order to also take the score into account. So instead of considering only the travel time, in this case 2 hours to go from A to B, we will subtract, because we want to maximize the total score of the trip. So we will subtract a weight mu that depends on the heuristic, on the algorithm that we applied, multiplied by the score that is associated with visiting or stopping, not visiting, but stopping point B. Okay? So in this case, the weights that we will actually use in the A star heuristic for maximizing the profit, and maximizing the profit is because we are interested in maximizing the score of the trip. So the weights that we will actually use are these discounted weights. Okay? So we now have a few results for two sets of instances, one for smaller instances where we compare the heuristics with the exact solution given by the heuristics with the exact solution given by the integer model, and then a larger set. So in this first, these are the results for some of the results for the small graphs. And here we can basically say, so in the first column we have the total trip time for the shortest path problem. The second one, it also refers to the shortest path problem, but where we made a few changes. And what we can see in this case, so first, the solutions obtained by the A-star search were refined using a mixed integer formulation, and namely, we have created another shortest path model or problem where we forced the arcs in the final solution the A-star heuristic with the discount prices or the discount scores, to be in the solution. So we can see that the total trip times obtained by the two approaches are more or less the same, are very similar. But when compared to the shortest path problem, the total trip time increases on average in 3.3% when the refined shortest path model is applied. Also, so still for the small set of instances, in average, the A-star with discount, which is this ASDM, has shown on average 11.9% worse scores with respect to the optimal solution that was found by the integer model. This value is fairly large, especially because it's not this is an average value, and some of the values are fairly big. For instance, this one is 33%. Okay. But on the other hand, the runtimes are quite small. Of course, in this case, the runtimes for solving the integer problem are not very large either, because we are considering the small graphs. But if we increase the size of the graphs, what happens? It's almost
1 minute to finish.
Yeah. Okay. I just have 2 more slides. Thank you. With some more results, and in these 2 slides, the idea is to compare 2 heuristics. So just the plain A-star method with the A-star considering the discounts, the scores, so taking them into account as well. Here we use 2 different weights, weight 1 and weight 2, and we can see that in this case the total score of the trip increases a little bit, especially with respect to just the plain A-star algorithm. Also, the A-star algorithm is slower to run, and when comparing the total trip time, we can see the total trip time. We can see that when we take the scores into account, the total trip time, as expected, will also increase. In a way, it's a big criteria problem, and this is mainly what I wanted to present. So if there are any comments or questions, I will be very happy to answer them. Thank you for your attention.
Okay, thank you again for your presentation.
You're welcome. Thank you.